I don't know how to use the laptop.
Okay, so you're ready. So our next speaker is Amelia Livingston, who's a student at the Imperial College in London. And she will talk about definitions, asking where are there some more equal than others.
Thank you for the introduction. So for my master's thesis, I am formalizing in Lean some maths I learned over the summer. And it's in the area of early uses of homological algebra in algebraic geometry. So as they say, algebraic geometry is about zero loci of sets of polynomials. And in general, these polynomials are not going to be of degree 1. And so in that sense, you could call algebraic geometry non-linear. And in the 50s, people started asking whether you could use homological algebra to sort of linearize problems in algebraic geometry. So for example, an affine curve is characterized by a quotient of a polynomial ring. And instead of studying this ring directly, we could instead analyze the modules over the ring. And one way to do this would be to derive certain chain complexes of the modules. So a chain complex is a sequence of our modules with a sequence of our linear maps. And the maps have to map into the kernel of the next map. So if you compose any two consecutive maps, then you get the zero map. And then what we do is we take the homology of the sequence, which means modding out the kernels by the images. And so you're measuring how far the images are from being the whole of the kernels. And the homology ends up telling you loads about the modules and in turn about the ring. And in my context, a particularly useful kind of chain complex is called a causal complex, and that's what I'm trying to formalize. So from the definition, you can see that the ingredients in such a formalization are going to be formalizing the modules and formalizing the maps, and then having a way to manipulate chains of modules in Lean. So the modules in a causal complex they look like the thing on the right. And the thing on the right is a quotient of the thing on the left, which is called the tensor power. So we should formalize that first. Now, a tensor power is a kind of tensor product, and the tensor product is generated by ordered pairs of elements of M and N, modulo relations that guarantee that tensoring distributes over addition in both arguments, and that it commutes with scalar multiplication. And these relations turn out to be precisely the relations that give you the fact that if you've got any map out of M cross N that is linear in both arguments, then it's going to factor uniquely through the natural tensoring map. And that's the universal property of the tensor product. So tensor products show up everywhere. The localization of a module is the tensor product of the module and the ring localization. Polynomial rings are tensor products of smaller polynomial rings. And then a particularly useful example is that if you tensor together two free modules, you get another free module. And indeed, like most people first meet tensor products in the context of free modules, in particular in vector spaces. So the nth tensor power of a module is just the tensor product of M with itself n times. And the 0th tensor power is just a base ring. And that's not just by convention, that's by things. So let's look at our useful case for a minute. If you've got a free module and a basis of size n, then this is going to induce a basis of the mth tensor power just by taking m tuples of the basis elements. So you can have repeated entries, that's fine. And the tensor product isn't commutative. So E1 tensor E2 is not E2 tensor E1, and they're linearly independent. So ultimately, you get a basis of size n to the m. And looking at a little familiar example over a real vector space of dimension 2, if we try and take the second tensor power, then it's just the basis is just all the ways of tensoring together the basis elements. And so we end up with a vector space that's isomorphic to R4. And here are some of the elements, what they look like. So the tensor product acts quite a lot like multiplication in that it distributes over addition, first of all. But there's something different about it in that if you say tensor together two elements of M, then the resulting object is not in M, it's in a new type called M tensor M. And certainly in Lean 3, at least, mul is a homogeneous operator. So we can't call the tensor product multiplication in Lean. So what if we wanted to find a module containing M where we can call the tensor product multiplication? We're basically asking for this module to be a ring as well. And one thing we'd need is multiplicative closure. So we need to contain all the elements like M tensor N tensor M, or M tensored with itself 4 times. Basically, we're going to need to throw in all of the tensor powers. And actually, this is all we need to do, because if we take the direct sum over all of the tensor powers, what we end up with is something that's an R algebra. It's called the tensor algebra, and it's already in MATLib. So that's great. We can just go and have a look at the API. So in MATLib, the tensor algebra is a quotient of some inductive type. And this inductive type, we ask for it to contain M, we ask for it to contain the ring, we ask for additive closure, and we ask for multiplicative closure. And so from this definition, it's quite clear that this is sort of the smallest R algebra containing M. It's like the left adjoint to the forgetful functor from R algebras to R modules. And then we quotient by the exact relation that gives us the universal property, which is that if you've got a linear map from M to some R algebra A, then that is going to induce a unique algebra map out of the tensor algebra through which the original map factors. And you can't see any mentions of tensor powers here, but universal properties characterize objects up to unique isomorphism. So surely we have everything we need to sort of analyze the tensor algebra internally. And certainly we have some things for free. We can easily define the natural multilinear maps that send n tuples of elements of M to their tensor product in the tensor algebra. But what about accessing the direct sum decomposition? What about looking at seeing that the elements look like elements of a direct sum? Well, I tried to prove that the spans of the images of the maps MUC have trivial intersection, and it was messy and equivalent to just defining the tensor powers independently and then injecting them into the MATLib tensor algebra. So I decided to try and do that. And if all definitions are equal, it should be possible to define these things independently and then prove that they inject in, like just using the tensor algebra API, which is mostly just the universal property. So let's build these things. We can do it inductively. But this pseudocode is not going to compile because at sort of the inductive step, tensor product needs a R module instance for both of its arguments. And if we're trying to define a function that just spits out a type, then all we know about the nth tensor power here is that it's a type. We don't know that it's an R module. And so one way around this is to use the category theory library, where you can instead define a function that spits out something of type capital M module. Or we can define an auxiliary type that spits out sigma type that is sort of a tuple of your tensor power and then the relevant instances. And so that's what I did. This is pseudocode, but it means you can feed tensor product explicitly the relevant instances. And then once you've done that, you can very easily show the universal property, which is that n linear maps factor uniquely through linear maps out of the nth tensor power. But now we need to inject these objects into the tensor algebra. And it's easy enough to define the map because you just apply the universal property of the tensor power to the n linear maps MUC. But when we're proving injectivity, we only have one thing at our disposal. We only have the universal property. And if you look at it, applying the universal property is always going to involve picking some algebra A. So here's one algebra you could pick. You could prove that the direct sum over the tensor powers is an R algebra, which is going to take some work. And then set A to be that, and the statement is trivial. But if you're going to do that, why didn't you just define the tensor algebra to be the direct sum in the first place and do the work then? So if this quotient definition is worthwhile, we kind of want there to be some clever algebra we could pick. That means the work involved in proving injectivity is either different or less. And I tried to think of one. There's a recent thing in MATLib that puts an R algebra structure on R direct sum M. But that doesn't help and the sticking point ends up being that there's no sensible linear map from M to a random tensor power of M. I also tried using the endomorphism ring of M, that didn't help either. And yeah, ultimately, I don't think there's a way to do this. I think MATLAB's definition is by design the least detailed construction to give you the universal property, and beyond that, you don't get much else. So we're going to have to do some work. One thing I think you could do is develop a theory of graded algebras, and I'm not doing that at the moment. I just directly proved that the direct sum was an R algebra. So that involved showing multiplication well defined and then proving the axioms of an R algebra. And the hardest thing seemed to be multiplicative associativity. That was quite painful. But once you've done that, you have much more at your disposal. You have, first of all, the universal property of the direct sum, and the universal property of tensor powers, which is the universal property of the tensor product in disguise because of how we defined it inductively. And we've also got something else, because I suspect that if all you knew about the tensor product was its universal property, I think you probably still have to do some work to talk about tensor products in the way you want to. Like, I think it's probably a similar situation. And in MATLAB, there's a nice big API for tensor products where I guess this work has been done. And so I think between all of these things, a big API and 2 universal properties, I think that gives you enough to have a robust API for the tensor algebra and its direct sum decomposition. And so then you can quite easily define an R algebra isomorphism between the direct sum and the MATLAB definition. So here's another example when the universal property doesn't quite give you as much as you might hope. When we learn about ring localizations, we always do it by constructing them. So we pick a submonoid S, and we mod out R cross S by some equivalence relation. And then we have to do some work to prove that the resulting object is a ring. And then we get the universal property, which says that the localization is the unique map such that certain ring homs out of R will factor uniquely through the localization. But suppose this is all we know about the localization. Then we don't have to do any work to show that it's a ring because it's automatically a ring. But what if we want to talk about the elements in the way we used to, in using the standard facts that we would get from construction? Well, the only route we have to prove these things is the universal property. And if you want to apply the universal property, you have to pick some ring A. And you can probably convince yourself that the only A's worth picking are at some point going to involve doing steps 1 and 2. So you're doing the same work, but just at a slightly different point. Oh, but I think also the tensor algebra situation is kind of even more frustrating than this, because in that instance, you have actually constructed a model. You have built this inductive type and you've found some relations to quotient by, so you've got this construction and you've got a universal property, but you still don't have enough to prove the basic facts that you want. And I think that's because the construction is by design the minimal construction to give you the universal property. So, of course, there's loads of situations where the definition you pick affects how easy it is to prove things, but I think they're often of a different flavor. So with the real numbers, if you build them with Cauchy sequences, then proving the axioms of a complete Archimedean field, I think the hardest bit is proving the existence of multiplicative inverses. And then with Dedekind cuts, I think the hardest part is proving additive associativity. And so these are different constructions creating fundamentally different obstacles. And you can see with both of these constructions, they're kind of meaty. They've got some idea behind them. And it's quite a different situation to minimal definitions that just shuffle work around. So we've got this robust API for tensor powers now. So we can define the modules of interest, and these are called exterior powers. And they're a quotient of the tensor powers. So the tensor product induces this map called the wedge product. And again, it acts a lot like multiplication. And so to exploit that, we're going to have to map into a larger type. And if we just take the direct sum over the exterior powers, this also happens to be an algebra. So it's called the exterior algebra, and it's the quotient of the tensor algebra by some two-sided ideal, which is generated by elements of M tensored with themselves. So let's see the wedge product in action. if you've got x and y and m, then since x plus y wedged with itself is 0, then if we apply distributivity and the relation, we get that x wedged with y plus y wedged with x is 0. And so you have that the wedge product is anti-symmetric, and that the exterior algebra is sort of the smallest algebra containing M where this property holds. So let's look at our example case again. If M is a free module and you have a basis of size n, then again, this will induce a basis on the mth exterior power, but it's a slightly different basis. This time we can't have any repeated entries. And also, if you've got the same M tuple and you order it in a different way, you commute it and then take the wedge product of the basis elements, they're not going to be linearly independent. And we'll see why. But this means that you have to pick sort of one permutation for each M tuple. And ultimately, this gives you a basis of size n choose m. So in a little example, if we have the real vector space R3 and we try and calculate the third exterior power, well, first of all, in the third tensor power, we're going to have basis elements like E1, tensor E1, tensor E2. And because we're modding out by something that's multiplicatively closed, this is going to go to 0 in the third exterior power. And so will any other tensor products with repeated entries. And on the other hand, if we have a wedge product of 3 distinct basis elements, then if we just repeatedly apply the anti-symmetry, then we end up seeing that these two wedge products are the same up to multiplication by the sign of the permutation. And so they're not linearly independent. And so any basis is going to be generated by one element, for example, that. And you get a vector space that is isomorphic to R. So exterior powers are, in the vector space case, very useful in differential geometry, because if you have a smooth manifold and you take a point on it, and then you take the tangent space at that point, and then you take the pth exterior power of the tangent space, then you can use this to define the space of differential p forms at that point. So it's quite a desirable object to formalize. And the exterior algebra is also a MATLAB, but as you might imagine, it's defined as the quotient of the MATLAB tensor algebra. And so we don't know that much about it, but we do know the universal property, which is if you've got an R linear map out of M to some R algebra A, satisfying the relevant property, then it will factor uniquely through an algebra map out of the exterior algebra. And in comparison, the universal property of the exterior powers has a bit more meat to it, because it says for all n multilinear maps where they map to 0 if some of the entries are the same, will factor uniquely through a linear map from the nth exterior power. And the Fs, the maps in this statement, are called alternating maps, and a good example is the determinant of a matrix, where the arguments are the rows of the columns. So now that I had like a nice tensor power API, I was hoping I wouldn't have to do any work to define the exterior powers, but there is still a little bit more work to be done. And there's 2 ways you can do this work. So the first way is basically the MATLAB way of you quotient the tensor algebra by a 2-sided ideal generated by elements of M tensored with themselves. And this is a ring theoretic thing. So you keep all the information about multiplication, and the object you end up with is automatically an R algebra. But because the summands are just submodules, you sort of forget some information about them, and you have to do some work to prove the universal property of the exterior powers. And that work boils down to checking that your 2-sided ideal is actually the same as an R submodule generated by n-fold tensor products where some of the entries are the same. And then the other thing you can do is mod out by an R submodule in the first place, generated by precisely these elements. And so you remember everything about the summands, and you've got everything you need to know about the exterior powers, but you've forgotten stuff about multiplication. So you have to prove that it's still well defined and that you end up with an R algebra. But the work in this ultimately boils down to checking exactly the same statement as in choice 1. So something similar has occurred. We're doing the same work, just at slightly different points. And I chose route 2. And so now this is what a causal complex looks like. We have the modules and we have the maps. And the last ingredient is to be able to talk about chain complexes. And in my use cases, M is always a free module of finite rank. So in that case, most of the modules in the causal complex are actually trivial. And so in particular, I need a way to flexibly work with finite chain complexes. And this turns out to be a kind of a tricky problem, because if you index your complex with integers and you have two integers that are definitely equal, but they're not definitionally equal, and you want to use this fact easily, things can get quite hairy. And there are various ways around it. I know that Marcus Himmel was working on building an API to help you work around this by defining like complex glue. And also in the causal complex case, there's this nice fact that causal complexes are tensor products of smaller causal complexes. And so maybe you can use that to make things easier. And this would involve defining tensor products of chain complexes, which could use the monoidal category API. I don't really know. But that's the current status. Thank you very much for listening. Are there any questions?
Hey, thank you very much, Amelia. We can thank Amelia. Other questions?
So when you were making your own tensor algebra, you have to prove associativity, but that doesn't even type check, right?
It does when you've, yeah, because you prove, yeah, I had to define sort of, it's based on the tensor product, but it's defined as a bilinear map in the tensor algebra. So it does type check in the tensor algebra.
Oh, the full tensor algebra it type checks.
Yeah.
I see, but it's on the individual pieces that it doesn't.
Yeah.
Because you're making the whole thing at once, it's fine.
Yeah.
Aha. This is somehow Mario's trick. Did you make it as a sigma type?
No, as I use direct sum, so it's like d fin subs, whatever.
Aha. Yes, I see. But somehow, I see. D fin subs are somehow a generalization of Mario's sigma type trick.
Yeah.
Aha.
So maybe we should say this would be less Kabbalistic. We say d fin sub is dependent finitely supported functions for people attending casually. So Amelia, do you think we should remove the way the tensor algebra is done in MathLib now and replace it with something else, or in the end, are you happy with how it works?
I mean, I'd like to PR this stuff and add the alternative construction, but I don't think we necessarily need to remove the original construction. I mean, there's kind of benefits to having a very clean, minimal construction, maybe.
And maybe a related question. So if you do if we have a robust library of exterior algebra, should we just remove all those elementary definition of determinants? I mean, like with this, this ugly formula with expansion and permutation and stuff, and just define determinants like in Bourbaki, and just using the exterior algebra all the way through, never writing any sum of a permutation.
Again, I think, I don't know, but I think the general, are there other cases in MathLib where it's just good to have two different constructions and not unify everything, because like a bunch of the library will be, sometimes one's more beneficial for building something and one's more beneficial for building another thing, and it's just worth keeping loads of code and organizing it well. I don't know.
You just prove you have them both and prove the equiv or something.
Yeah.
Well, in this case, it's even an equality.
Equality, yeah.
Just the determinant of a matrix.
We were always told, that the way to build a maths library is you should work in the maximal generality possible, right? But then when you actually think about it, you realize that there is no maximal generality. And in fact, what it really means is you should just work in a very large generality, really. And, and so this is somehow the problem. You work in a large generality, you do some stuff, and then eventually somebody comes along and they're working in a larger one.
So I personally, as a user of determinants, I rarely use I rarely use this multilinear viewpoint. Even so, I know it's there and it's beautiful. I use permutations a lot.
I see. So you need access to the permutations.
Yes.
Whatever the definition is, you'll need access to the
Yeah, but there could be a lemma saying that the determinant is equal to a sum of a permutation, but the definition and all the main properties would be established using the exterior algebra.
Does it matter what the definition is?
I mean, it matters when you want to prove. So for instance, proving that the determinant is multiplicative, if you define the determinant using exterior algebra, it comes for free.
Right. But on the other hand, we probably have the proof that it's multiplicative already.
Yeah, but it's an ugly proof. I mean, using combinatorics. Can you believe that?
Well, you will use combinatorics anyway to work with exterior algebra. You cannot avoid having the sign of a permutation in there. Otherwise, it's not clear that the basis is a basis.
But if it weren't there already, there would be an argument for doing determinants like this. But because it's there already, is there a clear argument for refactoring?
No, I think we have better things to do.
Proof of relevance means that all arguments are equally ugly, right?
Sorry, Eric?
Proof of relevance means that all arguments are equally ugly once they're in a proof.
And we have one last question from Cyril about looking at alternative formalization, especially in Coq. So Amelia, did you look at what they do in Coq?
No, I did not. But yeah, I will have a look. How is it done in Coq?
So Cyril, is it in MathComp or in some other library?
Oh, they also have two.
Oh, they have many.
Cyril has no mic again.
Okay. I think Eric maybe looked at the MathComp formalization.
I don't think it was in MathComp. I did have a look at Theory's formalization.
The one before MathComp, okay. Theory's formalization.
Oh, he did that before MathComp existed?
Yeah, it seems so.
I didn't know that.